this is going to be the second video for this dynamic consumption model. And in this case, after just explaining how the two-period model works, we are going to focus on the infinite horizon model. That is just to expand the two-period model to more periods, just for infinite periods. Okay, there will be also some kind of other kind of changes in the model, but it is quite similar to two-period models. Okay, so let's start with this, and with this video, yes, we are going to finish this chapter of dynamic consumption model in order to understand how the consumption works in short-term fluctuations and how important it is in macroeconomics. Okay, so let's start with the infinite horizon model. Now we are going to expand the two-period model to the infinite horizon, as I said before. So first of all, I want to write some variables, okay, in order to understand how this model works. Okay, first of all, here we have to add beta. Okay, what is beta? Beta is the discount factor. Okay, this is the discount factor. Remember, discount factor, and by definition, beta is what? Is 1 divided to 1 plus rho. Okay, when rho is the preference rate. Okay, what else? This beta must be a number between 1 and 0. Okay, that's also assumed. Then we have another variable that is AT. We are going to change savings and we are going to add this A, that is assets portfolio. I'm going to explain now. It's just the net, by definition is the net stock of financial assets, or just the net stock of the portfolio that we have at the beginning of the period T. Okay, at the beginning of the period T. If this A is greater than 0, AT is greater than 0, then we know that households are net lenders. But if this AT is smaller than 0, then we know that households are net borrowers. So since AT plus 1 denotes the assets held at the beginning of the period T plus 1, then we have this is similar to the savings because it corresponds basically to the savings ST in the two-period model. Okay, so it's just a change in the notation and in the ideas. Now savings is some kind of portfolio. Okay, then we have, of course, the RT, that is the real interest rate of these financial assets of the portfolio, and then of course WT, that is just the wage that those households receive. Okay, perfect. And then of course we have an instantaneous utility function that is just this is the instantaneous utility function. Okay, and of course I'm not going to explain again the assumptions that this utility function has, but it's just the usual concavity assumptions. Okay, the increasing function, diminishing returns, and all that stuff. So let's start. The individual, the households wants to maximize the utility function, but now what's the utility function? Well, maximization of the utility function, yeah? And here, of course, we have a lot of variables. CT plus S, we have also AT plus 1, okay? Well, AT plus 1 plus S, and let's say that goes to infinity, and S equal to 0. Okay, so this is going to be to maximize what? To maximize VT okay, and this is going to be this, and I'm going to explain by right now, okay. What? Vita. Okay, let's say that we want to maximize this. Why this? Okay. Okay. In the first period, the household wants to maximize just the instantaneous utility that has. In the second period, wants to maximize also the instantaneous utility for the next period, of course, but we have to take into account the discounted factor here. Okay, then we have what? The discounted factor again, utility ct plus 2. So in the end, this goes till infinity, and if we put here the sum of all this to aggregate everything is just this formula, because this elevates to s and this will be equal to s. Okay, so it's just that. I think that it's quite obvious. Okay, so we want to maximize that instantaneous utility function. And what's the budget constraint now? Okay, now we are going to talk about the flow budget constraint, that is the following one. We have a t plus 1 plus s plus also the consumption, okay, plus the 1 plus real interest rate that of those portfolios that we have when s goes to 0, 1, 2. Okay, this is the budget constraint. Of course, we have consumption here. We have the assets with plus s for the next period. Well, 1 plus s. Here we have 1. This is this is the wage that we receive. This is the return that we got of those portfolios. So this is the present value of income, of the wage or wealth, and this is just what we are doing, the consumption, and this is some kind of savings that these portfolios, these assets are going to will go to the next period and will just create new returns. Okay, so I'm not going to write for each period. This is for this function of this budget constraint. Okay, this budget constraint applies for all periods. Okay, perfect. So in the end, in period t, in the beginning, households must choose what? Choose the entire future path of their consumptions and savings, given the information that they have, of course. Okay, so they are going to maximize this. So to maximize this, of course, we have a Lagrangian, as always, quite a long one now. Okay, because we have, of course, this. Just the utility function, okay, and now lambda for the restriction that we have for the budget constraint, okay, this is just wage plus s plus 1 plus rt, no, here rt plus s, at plus s minus consumption t plus s. I'm going to follow here minus those assets in t plus s plus 1. Okay, so this will be the Lagrangian function. So there is, this is the aggregate one, but in the end there is like a separate Lagrange multiplier for each period. Okay, So just we are going to delete this, and I'm going to write the first order conditions from this Lagrangian, this maximization problem. Okay, so the first order conditions here. So if we do respect to ct plus s, the first partial derivative, of course, as you know, is what? Is just vita is this derivative minus lambda t plus s. This must equal 0, and here if we do it for the assets in t plus s plus 1, okay, then what we obtain is just minus lambda t plus s plus lambda t plus s plus 1, 1 plus real interest rate plus s plus 1 equal 0. Okay, now you are going to ask here why this? Because here there is no lambda with t plus s plus 1. Okay, when we are doing this kind of partial derivative, take into account that we are doing at plus s plus 1. Okay, here there is only one, at plus s plus 1. Okay, so this minus goes with this lambda and is this. But from where do we obtain this? It's quite easy. We have to go to the next period. Why? Because in the next period this will change to at plus s plus 1. So we have to do also the partial derivative of this, that is just this. Okay, 1 plus real interest rate at t plus s plus 1, because we are changing all for the next period. Okay, we have to do like convert this budget constraint to the next period, and just we get this also plus 1, this would be plus 1, this would be plus 1. Okay, so when we are doing this kind of Lagrangian partial derivative, take into account this kind of changes in time. These changes are important because otherwise these first order conditions are not going to be right. Okay, so from here we can obtain what? Of course, the Euler equation. Okay, so Euler equation, or just the optimality condition. Okay, so I'm going to delete this, or just the optimality condition. So this will be what? Ct1 plus Rt plus 1, this equaling 1. So in the end, this is the optimality condition, the Euler equation, and it's not very different from the two-period model. I mean, we have the discounted factors, and then we have yeah, that's it. That's the main thing that changes here. Okay, so we have that optimality condition, and from this optimality condition, and also what? Also from the intertemporal budget constraint, we can obtain the consumption levels, the optimal consumption levels. So now we have to compute the intertemporal budget constraint. Okay, so let's go with that. Let's start with that. So the intertemporal one. Okay, the intertemporal one. Okay, let's do it by period. So in the first period we have like 80 plus 1 plus CT, wage plus 1 plus RT, and okay, in the second period we have 80 plus 2 plus CT plus 1, wage plus 1 plus 1 plus RT plus 1, AT plus 1. Okay, so we have to solve for AT plus 1 in from the period T. Okay, so I mean we can do just substitute then into this period T plus 1 budget constraint, and in the end what we obtain, what it is quite simple. It's just, well, it's just to do a substitution here of equations. Okay, so AT plus 2 plus CT plus 1 plus 1 plus real interest rate consumption T equals wage T plus 1 plus 1 plus RT plus 1 wage T plus 1 plus RT plus 1 times 1 plus RT 80. Okay, so yes, we have to solve 80 plus 1 from the period T budget constraint. This is from here, this 80 plus 1, and then just we just exchange it. Okay, we just change it, and that's it, what we obtain. Okay, so let's continue with this. Okay, so now to continue with this, what if we divide both sides by 1 plus RT plus 1? Okay, so what we obtain here would be just AT plus 2 divided to AT RT plus 1 plus CT plus 1 divided to RT plus 1. Okay, so this is what we obtain. And of course, we can do further substitutions again. I mean, with AT plus 2, AT plus 3, till AT plus T. I mean, T like, okay? So we can do all those substitutions. And doing all that, we obtain a more general form, okay? And that general form is going to be the following one. It's quite long, so I'm going to just... So it's just what? A T plus T. Okay, and here we have this by the multiplication is just multiplication. Okay, Q1 and this K. Okay, plus what? Another multiplication here with 1 S and 1 plus R T plus K. Okay, this must equal to, well, this must equal to T minus 1 is 0 wage in plus S period. Another kind of multiplication here. T plus K, okay, plus 1 plus RT 80 assets. Okay, so this is the general form if we do the same for that substitution again and again for each period. Okay, where, well, I want to put also that here this K equaling 1 and S minus 1 yeah, I can, well, to know, yes, that this by definition is, of course, but I mean, you know all that. Oh, sorry, this is multiplication, okay? Because this is not a sum, this is an aggregate multiplication. Okay, just I put this just to know what I mean, what this means really. Okay, but I suppose that you know it. So, we are going to let this t, okay, this capital T go till what? Till infinity, of course. Why? Because we want to compute the infinite intertemporal value constraint now. So this T, this capital T must go to infinity. Okay, so let's do that now. And in the end, if we if we put just that t goes to infinity, what we obtain is of course here again we must have that kind of aggregate multiplication because we cannot erase that. Okay, now to infinity, another multiplication here is 1 plus real interest rate in t plus k as before, and as before here also 1 plus rt assets in t. Okay, so we obtain basically that. Okay, but we have an additional constraint here in order to simplify this. Okay, so we are there now with that intertemporal value constraint, but now we know another thing. We know that the limit of t going to infinity of what? Of this discount factor t, a t plus t, and must go to 0. Yeah, and this I mean by assumption, as we know that of course this must be this because of those assumptions of the instantaneous utility function, then we can simplify this constraint basically to this, the discount factor with t power t, a t plus capital T, and this equals 0. Okay, and you will ask, why this constraint? Okay, it's quite simple. I mean, this constraint says that in the very distant future, the discounted value of asset, I mean, the discounted value of asset that is just this, must go to 0. And why? Because if it doesn't go to 0, it will be like an Ponzi game. Okay, so this constraint is known as no Ponzi game condition. Okay, and I mean it is simple to explain that no Ponzi game condition. It's just that households cannot finance their consumption indefinitely by borrowing. Okay, the Ponzi game is just to be borrowing indefinitely and go increasing and increasing. But I mean, in reality, households cannot do that. So this will be an Ponzi game, and this is why we need this constraint. Okay, so just combining these things, what we obtain is the following. What we obtain is the following. We know that this discounted factor is 1 divided to this multiplication, okay, of the 1 plus real interest rate in t plus s. Okay, so now that discounted factor vita t comes from here. okay, comes from here. Remember, this comes from here. Okay, so that's it. That's it. And from this intertemporal budget constraint, we can just, with this intertemporal budget constraint and the optimality condition or Euler equation that we just computed before, combining these two as in the two-period model, here in the infinite horizon model, combining these two equations, we can obtain just the consumption functions, okay, the optimal consumptions. I'm not going to do that because otherwise this video is going to be really long, okay? But I mean, you can try it at home. It's just to put an example for that utility function, that instantaneous utility function. For example, in the two-period model, you can use assess constant elasticity substitution utility function. And here, of course, as we are dealing with assets and all these kind of things, this says function, constant elasticity function, converts to another one that is just the constant relative risk aversion function, that is CRRA. So that would be the instantaneous utility function that you can use it, and from that you can just start computing, first of all, the budget constraints. With those budget constraints and that instantaneous utility function, compute the maximization problem of the household, just obtain the Euler equation that will be just similar to the one that we computed here, and then you can compute the intertemporal budget constraint, and combining these two equations you will obtain just the consumption function. I mean, I can just give you the answer for that CRRA function, okay? So the answer of that consumption function, if you compute it, is just CT equals what? 1 minus beta. This is aggregate wealth, okay, remember that. And this, I mean, it's just the same, but we put here the rate of just the rate of preference, time preference, okay, that is raw, this is raw. But this is, you remember, the present value of the wealth, the aggregate wealth, okay, just to simplify the equation. So that would be the answer if you use, as an example, a CRRA and a constant relative risk aversion function, okay? So that's it. This is how we compute the infinite horizon model. It is a little bit more complicated than two-period model, but it gives you a good analysis of what happens in each period. And now you cannot just deal with two periods. You can deal with 3, 4, 5, 6, 20, 30, infinity periods, okay? So I think that is quite useful in order to compute the consumption function in that kind of aggregate level in these short-term fluctuations. Okay, so thanks.